Started. All right, so tonight is going to be the first talk in a series of 2 about the topics of decision trees and random forests. Tonight will mostly be focused on decision trees, while in the next study group we'll focus on random forests. And basically both are supervised machine learning models. And these will be some of the first ones you guys will learn. Does anyone happen to know the difference between supervised and unsupervised learning?
Supervised is when you provide it what it's looking for, whereas unsupervised is trying to figure out insights and what it's looking for in unstructured data.
Yep, that's a good explanation. Basically, supervised is either regression or classification. We give it some value it's trying to predict or some set of classes that it's trying to classify. All right, so a decision tree. Here's an example of one. This is to determine whether or not, or what type of contact lens someone should be prescribed. So whether it's none, a soft lens, or a hard lens. So it basically breaks down all the different features into trees that branch off in different directions, with the options being the branches. So for example, astigmatism, either yes or no. And you basically follow down the tree until you get to one of these final leaves that tell you what class is being predicted. So for example, going from the top, if you have normal tear production, then you go here. If you have an astigmatism, you go here. And then your age, I'm actually not sure what these two terms mean, but we'll just say if you go to the left-hand one, then you would be prescribed a soft contact lens. So it's basically a way to build a tree of decisions, hence decision tree, that can lead you to your different outcomes. So there's 2 main algorithms for decision trees. We'll cover both of them. One is a little bit newer and used more often, but you should still probably understand both. So the first and the older one is ID3, which stands for Iterative Dichotomizer 3. This is mostly used for classification only. And then the second is CART, which stands for Classification and Regression Trees. And from the name, it can be used for both classification and regression. So to start with, ID3 has 2 main concepts you have to understand. The first is entropy. So entropy is kind of a science term. It's used to mean chaos usually. So the more entropy, the more chaos. So in terms of decision trees, entropy deals with the distribution of classes. So this shows kind of different scenarios where we have 2 classes, plus and minus. We can see in cases where it's all pluses or all minuses, the entropy is low. But the more mixed it gets, the higher the entropy. So the more mixed your classes are, the more entropy there is, the harder it is to separate them. This is the formula to calculate entropy. You have basically the proportion of one of your classes times the log of the proportion of the class. And then that's summed for all your classes and then multiplied by -1. And this is how you do it in Python. So you can see the whole thing's -1. So this would be if we have 2 classes. Let me get the annotate going here. All right, so we're going to have 2 classes. So we have X's and O's. And we're just going to have 3 X's and 3 O's. So the E of X is just going to be 3 out of 6. So that's 1/2. And then the P of the O's is also going to be 1/2. So then we can plug those into this formula, and this is what we have here. So this part here is for the X's, and then this part here is for the O's. And then if we go ahead and run this, just to give you an idea. So this is only with, this is actually a different scenario. So this is if we had 1 X and 1 O. If we had the 3x's and 3o's, we actually, well, I guess it would do the same thing. But so you can think in this example, it's like having 1x and 1o. And we need to import NumPy here real quick. Import NumPy as NP. All right, so that gave us an entropy. If you remember on this curve, it's from 0 to 1. So we were at like 0.6, so that's like medium to high entropy. But now we can kind of change these numbers. So let's say one class is 2 out of 3. And then the other class is 1 out of 3. So now it goes down a little bit. If we take this to a more extreme end, we could do if 99 out of 100 are one class, and then 1 out of 100 are the other. Now we have a much lower entropy because the class distribution is much wider. You know, we're more towards down one of these ends where it's mostly all one class or the other. All right, so that's entropy. The other topic for ID3 decision trees is information gain. And this is basically the reduction of uncertainty that we get about our target variable given an additional feature. So in other words, it's the difference in entropy of our target variable minus the entropy once we add one of our feature variables. So it's kind of like the change in entropy. So we want to increase this because we want to decrease the overall entropy. All right, so building a decision tree from scratch using this algorithm. This is just going to make a data set for us to work with. Go ahead and run it. So this would be like for loan prediction. We have 3 features: older than 30, occupation, and income over 80,000. And you can see the different values here. So to start, we need to, our target class is approved. So we need to calculate its entropy. So we're going to count up all the times where we have approved and then all the times where we have not approved. And then we're also going to check the total size of our data frame and just store those there. So then we're going to calculate the entropy. This is that same formula from before. So we have our approved out of the total and then our not approved out of the total. And that gives us an overall entropy of 0.67, which could be expected because we have, 2 approved and then 3 false. So it's kind of similar to those examples I showed. All right, so then we have to go through each feature, calculate its entropy, and then subtract that from the entropy of the approved, our target, and see which one basically gives us more information. So we're going to start with age. So age is either true if older than 30, false if younger than 30. So what we have to do is count up all the times each occurs. So we can just get a data frame where we have older than 30 true and a data frame where older than 30 false. We're also going to need a weight. So basically the number of older divided by our total in the whole data frame, and then the number of younger divided by the total number of data points we have in the data frame. All right, and then for each of those basically class options, we have to figure out how many were approved and how many were not approved. So first for the older, we find the ones where approved is true, and then the ones where approved is false. Then we do the same for the younger. And now with all that information, we can calculate the entropy of both the older and the younger classes. So for the older, we calculate the older approved in this first part divided by the total number of the older class, and then older not approved divided by the total number of the older class. We do the same thing for younger. So now we have these 2 entropies for both of our classes. And now all we have to do is multiply them by the weights. So basically the proportion of that class overall. So in our data frame, let's see. So it was split 2 and 3. So the weight for true for older than 30 would be 3 out of 5, and then the weight for younger than 30 would be 2 out of 5. So that gives us our weighted entropies here. So entropy older times the weight older, entropy younger times the weight younger. And then we just add them together, and that gives us our overall entropy for the age feature. Now that we have that, we can just subtract it from the parent entropy, which is of just our loan approval, approved or not approved. And then if we run this, we will see our information gain for this feature of age. So that's kind of step one. Now all we have to do is repeat this for the next 2 features. So to do this, we'll make a function to make it a little bit easier. This calculates the entropy given the number in the positive class, the number in the negative class, and then the total number of that class. All right, so we're going to do occupation. So if you remember from the data frame, there's actually 3 different occupations. So we're going to have to do a list comprehension here. So in this first part, we get a list of all the unique occupations. I think it's doctor, lawyer, truck driver. And then we just grab a data frame that has only each of those occupations in it. Then like before, we have to calculate the weights. So the number of occurrences of each of those occupations divided by our total length of our data frame. And then for each occupation, we find the number that were approved and the number that were not approved. And then we calculate the entropy, basically, for each of those, multiply them by their weights, and then sum them all together. And that gives us our total entropy for occupation feature. And then just like before, we subtract that from the entropy of our loan approval, the parent, and that gives us this information gain here. So comparing that, so we had 0.15. Here we have more information gain. So far, this looks like our best next feature for branching. Now we just have to do it for the last one, which is income. This is almost the exact same code as for occupation. You know, we go through, we get the weights, we get the number approved, not approved, and then we calculate the entropy and calculate the information gain. So that one we have 0.29. So it looks like occupation is going to be our first branch. I think this just prints them all out here. So yeah, so using occupation as our first split in our tree will give us the most information. So let's see here. All right, so far what we have. So our first box at the top of our tree is going to be occupation. And it's going to split into 3. So we have truck driver, lawyer, and doctor. So now we treat each of these as a parent node and basically repeat the process. And now we have to look at income and age for the truck drivers, income and age for the lawyers, and income and age for the doctors, and decide the next branch in each of those. So it could be for truck drivers, our next branch is income, because we would gain the most, I cannot write, because we would gain the most information with that feature. So income. And then for lawyer, it could be the age is actually the highest information gain. So we have to kind of break it down for each one. All right. So what we're going to do is go through each occupation, and then we're going to calculate its total entropy, the parent entropy. Then we're going to find the entropy of age, the feature. and then the entropy of income. And then we calculate the information gains, and then we'll compare them and see for each occupation which feature is the next branch in our tree. So I think I'll have to close out so we can see this. So it looks like for all three, income is actually the next best feature. So now, before we check our answers, what it probably should look like is we have occupation, truck driver, lawyer, doctor, and then so income less than 80K and then greater than 80K. And then that would be the same for the lawyer and the doctor. And then from that, we'll have all of our leaves at the bottom that will be either approved or not approved. And these could be switched. So maybe for truck driver, if it's less than 80K, then you're going to be approved. But for lawyer, if you're less than 80K, then you're going to be not approved. So it's not necessarily in the same order. All right. So to check our answer, we'll actually use decision tree classifier from sklearn. And then it has this neat function plot tree, so we can actually visualize what the tree looks like. So we'll go ahead and import that. And then we have to convert all of our features to categories because we're using a classifier and that's the input that it needs. And we will just fit that classifier. So our features here, so all the columns except approved, and then our target, which is approved. You'll notice for criterion, we have to put entropy because the default will actually make it use the CART algorithm. So this makes it use the ID3 algorithm. All right, and then we can just plot our tree here to run it a second time. All right, so this actually found a different split for our tree. So can anyone, just from looking at this, guess what this is telling us? So if you start at the top, it says income over 80,000. So you can see the 3 and the 2 here. So if we print out our data frame, let me just close out of this.
Should we all be getting different numbers? Because I got occupation at the top of mine.
Oh, really? Did everybody get occupation at the top?
Mine looks like yours, Matt.
Mine looks like yours.
Me too.
Mine says occupation on top.
How do you check the version? Thinking we might have different versions of sklearn. If you guys can just run this, so just import sklearn and then sklearn.version.
I got the same version.
But you got different results.
Yeah. It's like those two are just swapped, the occupation and income.
Oh, now I got it switched. Interesting.
I still got income.
I guess, let's see. I think there is some like automation built in that we'd probably want to disable so that we, oh, let's try random. Yeah, there's a random state. So if you do random state equals 4, maybe not in there, actually in this part. Now everyone should get the same.
What do we need to set random state to?
Just do 4.
Why the result change when?
Because I'm not sure exactly how this function calculates it. I assumed it did, the basic algorithm, but it must have some randomness in it, which is why we have the random state option. So by setting the random state all to the same, it'll make sure any random numbers it generates are going to be identical, and then it'll give us the same output. But in this case, it split it on income first. So if the income is over 80,000, let's see, what's our data frame? So if it's over, to the left is yes. So automatically, if you're over 80,000, then it's going to predict approved. And then if not, it'll look at occupation. And let's see. So from there, the ones that are income under 80,000, there's only 2 possible occupations. That's why we have 2 branches here. So either the 2 or the 0. And I assume, let's see, so 0 is probably on the left, let's see. Yeah, so 0 would be on the left, and then 2 would be on the right. So if it's occupation 0, then not approved, and occupation 2, then approved. So these aren't the easiest decision trees to read. There are a lot of parameters you can change in the plot tree. So we might want to look into that a little bit to see if we can get it a little bit clearer to understand. But basically, it's doing something similar to what we did with the calculations. It just probably has an extra step or 2 that kind of made it split a little bit differently. But both would probably give similar results. So let's go on here to the activity then. I guess before we do this, does anyone have any questions? Did we go through those calculations too fast?
Can you just repeat again that last part? When you look at the occupation, if it's 2, then it's not approved. I missed that part. I'm sorry.
Okay, let's see. So here's our data frame. So remember, we changed everything to categories. So once we split on income, and on the right-hand side, that's income 0. So that's only these rows here. And in that case, we only have 2 possible occupations, 0 and 2. And let's see. Actually, I think this is reversed, yeah. Okay, so the number at the top of the block, like the 2 and the 3 here, tells you how many classes it broke down on each side. So we have 5 at the top, then 2 and 3. So income over 80,000. That actually does not make sense though, because it should only be the ones. Let me double check on this. For now, let's just rely on the actual calculations. I think there's like another setting or 2 in this to make it duplicate what we saw. So while you guys do the activity, I'll look into that. Okay, so the activity then. So you'll use the data scientist CSV, and you're going to basically perform the calculations we did with the ID3 algorithm to predict whether or not someone is a data scientist. So the goal is to do those calculations, decide where to make your splits, and then you can just do a little drawing of what you think the decision tree should look like. And then once everyone's done, I'll have a way for us to check it and see if we can match up the plots. All right, so I'll go ahead and break you guys up here. All right, so I figured out what was going on before, why we were seeing kind of different results than what we calculated. basically sklearn, in implementing the ID3 algorithm, it wants all the features to be binary, to only have two options, and it will actually convert them to binary if they're not. So that's why here occupation got switched to less than or equal to 1.5 or greater than or equal to 1.5, because here's the occupation value 0, 1, or 2. So it basically split it into binary. So then we have 3 on the left, which is the ones that are less than or equal to 1.5. So 0 or 1, which is 1, 2, 3. And then on the right is greater than 1.5, which is 2. And so the weird thing that happens when you make occupation binary, it actually has the same information gain as income. So that's why when we kept running it, they would flip back and forth. So I'm still looking for a way to do the classic ID3 algorithm and have non-binary features, because there should be a way to do that in Python. But if you do the calculations by hand, you'll arrive to the right answer that way. And I'm still trying to find a way to kind of show like on which side, but basically it's to the left is true. So like the condition is at the top. So to the left will be true, and then to the right will be false. So that's why occupation less than 1.5, you just have to look at the values here and see which way it goes. All right, so let's go here to cart then. So the truth is you probably won't use ID3 that much. Cart is kind of the default in sklearn and basically the default everywhere else you go, because it can handle classification and regression tasks. So it's really similar to ID3. It's kind of the same process. It just uses a different formula instead of entropy. And that formula is actually called Gini. And it's basically a sum of all the squared proportions. So we don't have the proportion times the log of the proportion. We just have the proportion squared. So it's just a slightly different calculation. And then instead of just being multiplied by -1, it's actually 1 minus that sum. So just different formula, but same kind of basic method that you would go through to calculate it. So we've been talking about decision trees for classification, you know, whether you're a data scientist or not a data scientist, approved for a loan, not approved for a loan. But we can also use it for regression to predict continuous variables, such as prices, things like that. So for this, we're going to make a data set here. This will make a regression data set with 10 rows in it, 2 features, and then the random state is just so we all get the same one. We'll make a data frame just so we can see what's going on. So we have our 2 features and then a target that we're trying to predict. To implement the decision tree regressor, we just import it from sklearn. And then like all the other models from sklearn, you just fit it and you pass in your X and your Y. So our models fit. Now we can kind of see what happens when we plug in a bunch of values and see what it predicts. So this basically takes all numbers from -3 to 3 and picks 100 of them within that space for each of the features, and then it'll just make predictions. So if we go back to our data frame here, basically these are standardized, so they're all basically like -3 to 3. So that's kind of why I chose that range. But here's the thing to understand about decision tree regressors. So here I have all of my targets, all of my Y values, and then here I have all of my predictions. You can see how many I have by doing this. So length of heads. So I have 10,000 predictions here using all different combinations of values for the 2 features. So if I run this, this will grab all the unique ones in our original target and then all the unique ones in our predictions. And it'll tell me whether they're true or false. So does somebody have a guess on what I will get when I run this cell? Anyone?
True, but I think I cheated.
Yeah, if you run it, it'll tell you. Yes, it's true. Does anyone have any idea of what the implication of this is? So
To
what
me, it
what-
means that whatever we're using to predict is exactly accurate 100% of the time.
Close. Basically, it's saying that our decision tree regressor can only predict the values that we gave it. So out of all these 10,000 predictions it made, it only made predictions that were in our training set, even though our targets are continuous. It only can predict a value that it's seeing. Because if you think of it like the tree, it can't have a leaf for every value from 0 to whatever, all decimal places. So it basically makes a leaf for each of the values it's trained on. And then when you pass in a new feature or a new data point at the top, and it gets down to a leaf, it can only be one of the values that it was initially fed. So that's kind of a downfall of decision trees. We'll get into some ways around this, but that's just something to keep in mind about it. And yeah, this is just summarizing it. So decision trees for regression can only predict the values that are in the training set. So if you want to predict values outside of that, if you have a range and you want to predict higher values, you won't be able to. So to make decision trees fit better, we can do some tuning on the parameters. They actually have a lot of parameters. So we will take a look here at the documentation. These are all the parameters you can change. So for example, max depth is the maximum depth of the tree. So basically how many branches down it will go at a maximum. Then we have things like min samples split. So the minimum number of samples required to split a branch into 2 nodes. We can have a max number of features. If we have like 100 features, we can limit that. Or we can just have it automatically pick. There's min impurity decrease, min impurity split. You can kind of read what all of these do, but basically changing them can make our model a better or worse fit. So you usually want to do some tuning on decision trees, whether it's a classifier or regressor. And the best way to do that is through grid search. So we're going to make a data set here. We're going to train just a baseline model on it, doing a train test split. So then we can see our train and test MSE and R squared, just to give us a baseline. So in this case, we're obviously, can somebody tell me what we should notice from these results about our model? Are there any red flags?
The R square declined.
Well, the mean square error on our train is 0, which means it's probably overfit, right?
Yep, and our R squared's 1, and then we can see we get much worse performance on the test. So we're definitely overfitted. So changing some of the parameters can help with that. So we're going to import a library called Grid Search CV. This basically lets us pass in a list of parameters, and it will try out every combination of those parameters, build a model for it, give it a score, and then tell us which combination ended up being the best. So you could fill this in with whatever you wanted. In this case, I just chose 4 features. The more features you choose and the more options you give them, the longer it's going to take to run. It'll kind of exponentially grow, so you have to be careful. But you can start off with something small and add more if it runs okay. So in this case, I just did the max depth, the min sample split, the max features, and then the min impurity decrease. And I just gave them a couple of different values and different ranges. Then you create an instance of whatever model you're training. So in this case, it's a decision tree regressor. And then you create a grid search CV model. You pass in your base model, which is our decision tree regressor. Then you pass in the dictionary of parameters. and then whatever scoring you want to use. So in this case, I'm going to use R squared. Verbose 1 will just basically print out a little bit about as it goes through each combination. And then you just fit it to your data set. So if you run this, it'll take a second. And we can see it did 5 folds for each of the 72 candidates. So it basically built 360 models with all those combinations. And from there, let's see if I have it. Yep, so from there we can just, off of that model, get the best parameters. So these parameters gave us the best results. So you can kind of save those and use those in your final model. What you can also do is just grab the best estimator, which will be the model fit on those best parameters off of the grid search. And if we do that, here's our train and test MSE and R squared. So we can see the test was a little bit better than before. The train is definitely a little bit worse, but that's a good thing because we were overfitted. We definitely still have some room to go here. You want to see both of these being a lot closer together. So we would want to add more parameters in our grid search and try out different combinations. But that's basically grid search in a nutshell. It lets you try out a whole bunch of parameters, find which ones are optimal for your model and whatever scoring you want to use, and can give you a way to improve over your baseline model. So now for this activity, which we're running late for, so this will probably turn into kind of homework. But you're basically going to use data in this disease prediction CSV to build a predictor on whether or not somebody has a disease. So you'll want to choose the right model. You'll also want to choose the right scoring metric if you're going to use Grid Search CV. So I gave you this link here. These are all the scoring metrics you can use. So in this case, we're probably going to do classification. So you have to kind of think, you know, what's going to be important. Do you value precision or recall more in this example? So you want to think about the real world case. This is predicting whether or not somebody has a disease. So that has kind of a trade-off on, you know, false positives, false negatives, that kind of thing. So yeah, you're going to build a model, use Grid Search CV, and try and fit the best one. And just to make this kind of a competition, when you do your train test split, do a test size of 15, and then do random state equals 4. That way everybody will get the same train and test sets, and then we can see overall who gets the best fit on their model and the best test metric. Does anyone have any questions before we begin?
I have a question, Matt. So the decision tree classifier is for when all the features are categorical values?
So the decision tree classifier can be used for any combination. So it can be numeric or it can be categorical features.
How about the regressor?
Same thing. They both take any form of feature.
So if in the data set I have a categorical value, I just need to turn that to a code, right?
Yep, so you just have to make it categorical basically, and that will work with sklearn. So if you just do like 2 category or 2 categorical, or as type category, whichever of those works.
And so what's the main difference between two, like regressor and classifier? Is it target variable, right?
Yeah, it's the target. So regressor, you're predicting a continuous value. Classifier, you're predicting a class. So
Okay, right.
false, you know, cat or dog, that sort of thing.
Cool.
All right, so I will.
Can you all see it?
Yep.
So I first read the data set and found there are 15 variables and 1 target. So next step is to construct the x and y, x being all the variables and y being the target. And because the target is a binary target, so either 0 or 1, so we should choose the decision tree classifier. And I said the random state equals 4. So I did import F1 score and recall score, and the baseline is here. So the train MCE is 0, which means that we are overfitting. And the test MCE is significant higher. F1 is 0.6 and recall is 0.63, which means like 63% of the true positives are able to be identified use this model. So next, we'll do a grid search. I changed the max depth to 5, 10. Let's try 15 because there are like in total 15 features. So the depth just means the height of the tree. It shouldn't be more than the number of the variables. And I also add mean weight fraction leaf. I think that's just the minimum weight a leaf can have. So in the grid search, my scoring is F1. So let me fit this. So the max depth I got is 5, which means like 5 features were selected. And so I'm able, the train MSE here is 0.24 and train F1 is 0.79. You can see that they are relatively close. Yeah, so that's it. We can also try accuracy score.
All right, good. Does anyone know why maybe recall would be an important metric to use in this case?
Yeah, so I tried that and figured out. So the reason you want recall is because you want to reduce the number of false negatives. Because you don't want to miss people that have the disease and tell them that they don't. The issue is that if you optimize your model to recall, it turns out it just predicts all of them as the disease, because then it's just maximizing recall.
Yep, I'm glad you uncovered that.
So if there were a way where we could minimize recall, that would be great.
Why would you want to minimize recall?
Because then you wouldn't pick everyone as having the disease.
But then
Well,
it would
never
pick
mind.
that no one has the disease. So
Never mind, I'm a crazy person.
Bonnie picking F1 is the best option probably, because it's basically accuracy, but it takes into account both precision and recall, and tries to kind of find a balance between them. So it can be good for a case like this. Might be a little bit different, you know, if it's like a rare disease and a small percentage of people have it. But in this case, it was like 50-50, so that worked. But F1's a good baseline, or just regular accuracy. You could use the recall though for your metrics still, so to compare your train and test. But for the scoring, you want it to be something like accuracy or F1, so it doesn't just predict everyone the same like that. All right, does anyone have any questions before we go? How's everyone feeling about the content tonight? Good, okay, not good?
Pretty good.
Good to okay, all right.
I feel
I
good.
want to say we'll be expanding on this, turning decision trees into random forests. And yeah, thanks everyone for coming. Have a good
Thank
night.
you. Have a good night.
Bye.